There's another rearrangement that's rather similar, and that's called the courteous rearrangement. So this one is the Hoffman. And the next one is the courteous rearrangement. And in the courteous rearrangement, what you do is you take an acid chloride and you treat it with sodium azide. And what happens is that the azide attacks the carbonyl carbon to give you a tetrahedral intermediate. And that then expels chloride. And so the result of that operation is to generate the substance that I'm writing up now, which is an acyl azide. Let's write that neatly. Acyl azide. Now these acyl azides, when you heat them, they rearrange and they give off nitrogen. And this intermediate is called an isocyanate. So that is the same type of intermediate that's generated in the Hoffman rearrangement. And in exactly the same way, if you treat the isocyanate with water, you end up, first of all, with this, and then that expels carbon dioxide and gives the amine. So it's another way of going from an acyl compound to an amine. You see in the Hoffman rearrangement, this bit here is an acyl group, but there's nitrogen there, so it's a special type of acyl derivative. It's called an amide. And in the courteous rearrangement, this bit here is again an acyl group. It's a special type of acyl derivative. It's called an acid chloride. And in the courteous rearrangement, you displace the chlorine to form an acyl azide. And that acyl azide then does something a little bit strange. And I need to show you one of the possible ways in which this is converted into the isocyanate. So what I will do is to make some room on the board. I'll clean off the names. And then I'll show you one of the possible ways of understanding what is going on. I'm going to write a different resonance structure just by putting the electrons, move the electrons like that. So I've got this resonance structure. Now, if this nitrogen leaves, it forms something called a nitrene. A nitrene is a neutral nitrogen stuck onto to one other thing. And this one other thing happens to be an acyl group. Now, this group R, with its pair of electrons, will move on to the nitrene, and the pair of electrons from the nitrogen will move that way. And so, if you follow that through, what you get is the isocyanate. Now that's all a little bit strange, and so I want to talk you through it again. I'll give you a moment to copy it down and talk you through it again. Now this isn't quite the mechanism shown in the book. And if you look up the literature, you'll find that the mechanism shown in the book sometimes applies, and sometimes this mechanism applies. But this mechanism is easy to understand. And so we'll just leave it with this mechanism. Now what's going on here? First of all, let's deal with electrons on nitrogen. Nitrogen has 5 electrons in its outermost shell. So, well, let me take a different color. Let's see if I draw some nice color. Yes, I've got red. You want to use green. Yes, you guys can see green at the back? Yes? Okay, nitrogen's got 5 electrons. Here's one of them. Here's 2. Here's 3. Here's 4. Here's 5. Now this one, there's 1. There's 2. There's that 2. 1, 2, 3, 4. But now, this nitrogen has got 6 electrons around it. Because 2 electrons there moved on to the nitrogen. So now it's negatively charged. It must be, because if nitrogen is surrounded by 5 electrons, it's neutral. If it's surrounded by 6 electrons, it's negatively charged. If it's surrounded by 4 electrons, it's positively charged. So this baby is now negatively charged. Now, you see, it's surrounded by 1, 2, 3, 4, 5, 6, 7, 8. Now I'm going to move this pair of electrons onto there. So this nitrogen has lost control over a pair of electrons. If you lose control over a pair of electrons, which you're sharing with something else, you've effectively lost 1 electron. If this is negatively charged and it loses 1 electron, it's got to be neutral. So now that nitrogen has got these 2 electrons. There it is. It's a neutral nitrogen. It's got 5 electrons surrounding it, if you count only those that originate from the nitrogen. And if I now take this pair of electrons and move it there, I will then generate a plus charge on carbon. But I can neutralize that plus charge by taking a pair of electrons from nitrogen, moving them here, so that the carbon now shares a pair of electrons. So it's gained 1 electron. It's lost control of 1 electron by these moving over there, but it's gained control of 1 electron by that pair moving into there. So the nitrogen, which is neutral here, is neutral there, except now the bond is different. Double bond, but now there's a double bond here, a double bond there. And this nitrogen now is surrounded by the appropriate number of electrons, because 1, 2, 3, 4, 5, 6, 7. That's wrong. Let me get this right. Nitrogen has got 5, 1, 2, 3, 4, 5. That's okay. And it should be surrounded by 8 electrons. So why isn't it? Oh, I've forgotten that pair. 1, 2, 3, 4. There it is. No, that's still wrong. Ladies and gentlemen, just let me think about this a little bit. How have I got mixed up? I'm sorry?
The R has we labeled the R as 2 electrons.
Yes.
You have 1 too many loans.
Just one man. 1, 2, 3, 4, 5, 6. So.
You don't need the 2.
1, 2, 3, 4, 5, 6, 7, 8. Now it's right, because that pair is moved there, so I've taken it away and I've put it into this region to form this bond. That's where it was. There we are. Now that's all nice hunky-dory, it's all fine. So that's the mechanism for this Curtius rearrangement. So in a Curtius rearrangement, you make an acyl azide and you heat it. It's right. It really is. You make an acyl azide and you heat it. And as a result of that, you get an isocyanate. And the isocyanate is attacked by water, and this piece comes off as CO2, and you liberate amine. Now, all that's probably a bit too theoretical for you, so let me show you some examples.
That fuzzy thing on the desk?
Oh God, what is it?
I don't know, but do you think it is his? What if it is a Tuesday?
Like, is this scarf or something? Or is this jacket?
How could that be a jacket? What a fabric.
A head wrap? It's a head wrap.
Supposing this is the problem, I want to make that amine, which is called aniline, as I told you in the past, and I'm going to make it from toluene. So what am I going to do? Well, I'm going to ask myself, what ways do I know at present for making amines? And one of the ways is the Curtius rearrangement. And the Curtius rearrangement, I know, involves an acyl azide. And so the question is, how can I make an acyl azide from toluene? Well, how do you make acyl azides? As I just told you a few minutes ago, you make them from acid chlorides. How do you make an acid chloride? Well, you make an acid chloride from an acid. And so working backwards, I really want benzoic acid. How do you make benzoic acid from toluene? The answer to that is simple. If you use alkaline potassium permanganate, you will oxidize that methyl group. So just by working backwards and asking yourself, how can I make such and such a compound? Well, you make it from another type of compound. Then, with this other type of compound, you ask the same question, how can I make that compound? And by working backwards, you see this, which is not immediately obvious. You can arrive at the method for making it by systematic procedure of asking yourself, do I know any ways of making amines? The answer is yes. Hoffman rearrangement, Curtius rearrangement. If I go for the Curtius, I need an acyl azide. If I go for the Hoffman, I need an amine. If I go for the Curtius, how do you make an acyl azide? You make from acid chloride. If I go for the Hoffman, how do you make an amine? One of the ways is from an acid chloride. So in either case, you have to make an acid chloride. You make that from an acid. You make it from an acid with thionyl chloride or PCl3 or PCl5. And so by systematically asking yourself these questions, you can work out the answer. And what you should do is you should do question number 20.7, which is the same as 20.8 in the 9th edition. Now, what are the reactions? I've told you now a number of ways of making amines. What are the reactions of amines? There are a few reactions that you ought to know about.
That's much bad reaction from Amy. Stop looking at the clock. That's so fast. Because I remember looking at it 5 minutes ago.
Okay. Yeah, his bio, for some reason, has been like,
It goes
faster.
so quick.
Yeah, because I like don't look at the clock ever.
I thought today, like, it would be even shorter. Like, it wasn't even shorter because of the evaluation.
Oh yeah. I'm like, it seems so lax right now.
I think it's because before maybe we were behind. Now we're like right
You
where.
have an acid. It could be hydrochloric acid, for example, or sulfuric acid. And you treat an amine with such an acid, the lone pair on nitrogen removes the proton from the acid, and you get a salt. So if you've done a reaction and you've got two products, one is an amine and one is not an amine, you can easily separate them. You just shake the mixture with dilute hydrochloric acid. The amine will become protonated, and the salt will then be soluble in water, and the upper stuff, which doesn't form a salt, will not be soluble in water. You can extract it with ether. And then once you've done that, you can take your acidic solution, which contains water plus your acid plus the salt of the amine. You can make it basic by adding, say, sodium carbonate. And once you've neutralized all of the acid, the amine will no longer be a salt. You'll just have the amine there. Now that'll be soluble in ether. So you can extract the mixture, get the amine into the ether layer, dry it, filter off the drying agent, evaporate the ether, and you've got your amine. Now I've written here a tertiary amine, but what I just said in the last few minutes applies to primary amines, secondary amines, and tertiary amines. So that's one of the things, one of the properties of amines, and everybody who's ever squeezed some lemon juice over some fish is using this procedure, because fish contain some amines, they don't smell very nice, and so squeeze some mild acid over the fish. The acid in the lemon juice makes a salt which is not volatile, you can't smell it. The other property of amines is alkylation. If you have an amine, and you treat it with an alkylating agent, now if one of these R groups is hydrogen, you can lose a proton and then get a non-charged species. But if all those R groups are alkyl groups, you get a quaternary ammonium salt, as it's called. A quaternary ammonium salt. And you remember that I told you this is not a very good way of making substituted amines, because if you start with ammonia and do it, you'll get first of all methylamine, but then the methylamine will react with more methyl iodide, you'll get dimethylamine, and the dimethylamine will react with more methyl iodide to give you trimethylamine, and finally the trimethylamine will react with more methyl iodide to give you tetramethyl ammonium iodide. So you get a horrible mixture. And you remember I told you that one of the ways of making primary amines is to use the Gabriel synthesis, which gets around this business of polyalkylation, as it's called. Many alkylations going on. The other, this is an example of the nucleophilic ability of an amine. But there's another type. Let me just, for argument's sake, let me just use a primary amine. If you have an acid chloride, you know that the nitrogen can attack the carbonyl and ultimately give you an amine. And if you start with a primary amine, you get a secondary amide. If you start with a secondary amine, in other words, 2 alkyl groups on nitrogen, then you have 2 alkyl groups on this amide nitrogen, and that is called a tertiary amide. You've got to be a bit careful with these words primary, secondary, and tertiary. Maybe I ought to clear that up for you. Supposing you have an alcohol. That's a primary alcohol. If you have 2 carbons on the carbon carrying the hydroxyl, that's a secondary alcohol. If you've got 3 carbons on the carbon carrying the alcohol, that's a tertiary alcohol. But what about amines? This is a primary amine. This one is a secondary amine. And that is a tertiary amine. What about amines? That's a primary amide. That's a secondary amide. And that is a tertiary amide. So for amides, primary amide means you've got nothing else on the nitrogen, just hydrogen. Secondary amide means you've got 1 carbon extra on the nitrogen and 1 hydrogen. Tertiary amide, got no hydrogens on the nitrogen. And for amines, it's the same thing. Primary amine has 2 hydrogens, secondary amine has 1 hydrogen, tertiary amine has no hydrogen. But for alcohols, it's the number of carbons on the carbon carrying the OH group. So the naming's a little bit confusing, you just need to remember that. Now, there's another reaction of amines which is most important in the case of aromatic amines, where the nitrogen is on a benzene ring. In other words, for aniline or substituted anilines. And I need to show you what that reaction is. Take an aromatic amine you get a diazonium salt. Now this is a very common undergraduate preparation, and if you do it in the lab, the chances are that it won't work for you if you allow the temperature to go above about 3 or 4 degrees centigrade. I've done this type of experiment with all sorts of aromatic compounds many times, and when I was a beginning undergraduate, first few times I did it, it didn't work. And of course, I blamed the recipe. There was nothing wrong with the recipe. What was wrong with me? I let the temperature get too high. And I remember telling the fellow who was in charge, but it was in ice, it was in ice. It doesn't matter if it's in ice. The inside of the flask could be red hot. You know, when they had this this big problem in Japan when the nuclear reactor went crazy because of the earthquake. You know, they squirted seawater all over the stuff. The outside was cold, the inside was pretty hot. So when you're doing this sort of reaction, you put a thermometer inside the floss, dipping into the floss. And then you know that the internal temperature is about 0. Then it will work fine. It's a beautiful reaction. Now, this is a reaction of a primary amine. This sort of reaction also occurs with aliphatic primary amines, but I'm not going to go into that. And part of the reaction occurs with secondary amines. I'm not going to go into that. I'm going to deal with the most important one, which is the diazotization, as it's called, of aromatic amines. Now, the reason why it's important is that this species is the precursor for a huge range of other things, many of which are in this room at present, because it's used in the dye industry. There are a lot of different colors that I see in front of me, clothes, so on. And so it's a very important reaction. What I first need to do is to tell you what's going on. I mean, it isn't magic, you know, that aniline goes to this diazonium compound. So what exactly is going on? Well, if you take sodium nitrite and you treat it with acid, you get nitrous acid. You get nitrous acid. If you protonate nitrous acid, you get the protonated species, and that gives water plus that material. Now, this material is attacked by the amine nitrogen. And when that happens, you get exactly what you expect. And then a proton is lost. Now I'm going to, instead of writing this ring, I'm going to use the symbol pH. So now I get this new intermediate species, which becomes protonated on oxygen. But what I'm going to do, because it's quicker to use this kind of method of drawing it, I'm going to draw it as I've drawn it there, to give that. Now what do I mean by all this? I mean that first the oxygen is protonated, so you get a new species. Then water attacks this so that you remove this hydrogen and these electrons then move that way. But I'm telescoping all that into this little picture whereby I pick up a proton here, lose a proton here, and the electrons move in the way that I've shown. The outcome is this. Now this thing is again protonated. It's again protonated, but this time on, again on oxygen. So let's protonate that on oxygen. Now, this oxygen is a good leaving group. The lone pair can come there. And you see I have now generated the diazonium salt by a series of protonations and then expulsion of water. Now, I said a moment ago that these diazonium compounds are tremendously useful. And I want to draw, I'll give you a moment to copy that down because I guess it is quite a lot for you. Well, I don't know if you realize that the early dye industry was the beginning of the pharmaceutical industry, because people working with dyes noticed that certain dyes will stain certain types of tissue to different extents. And so the idea developed that certain chemicals could stick to certain cell surfaces. And from that, the idea developed, well, if there was some organism that entered the body that was causing trouble, maybe you could find some dye that would just stick to the organism, it wouldn't stick to the cells of your own body, and would kill the organism. This was the idea that Paul Ehrlich developed, this idea of a magic bullet that could just hit the cells of the disease-causing organism. Paul Ehrlich was a rather strange fellow. He was very, very busy. He was very famous. Lots of people came to visit him. What he used to do to get rid of them, those that he didn't want, he'd say, I've got a very interesting phenomenon here. Here's something in which I've stained certain tissue. Would you like to try and see if the stain could be washed away? And of course he chose something where the stain stuck like glue. So the guy would go into his dressing room and hold the stuff under the tap, and after 10 minutes would get bored and would quietly leave. And that was how we got rid of unwanted visitors. Okay, let me now tell you some of the things that you can make from the diazonium salts. So I'm going to use a generic symbol for an aromatic ring. You can convert those things into a host of other compounds. What you can do is you can convert them into chlorides, bromides, iodides, nitriles, fluorides, hydrocarbons, and substances called phenols. So in other words, this group can be replaced by chlorine, bromine, iodine, cyanide, hydrogen, OH, fluorine. So straight away you see that there is a big range of possible products that you could make from an aromatic diazonium salt. And of course, since the aromatic piece could be benzene or a substituted benzene, there are many, many thousands of compounds that you can make via this chemistry. Now, these diazonium salts, of course, come from amines, from aniline. And the NH2 group stuck onto a benzene ring most frequently comes from a nitro group. As I told you in a previous lecture, if you take a nitro compound, you can reduce it to an amine, and then you can diazotize the amine. So nitro compounds are a sort of primary source for all of these other compounds by a multi-step synthesis. You take a benzene ring with some substituents on it, you do a nitration, so you've got the nitro compound, you reduce the nitro to NH2, you diazotize the NH2 compound to a diazonium salt, and from that diazonium salt you can make all of these. Now let me just tell you very briefly how you make each of these compounds. Supposing we have this amine, you can diazotize it to get the And if you treat that with copper chloride, you get the chloro compound. If you do the diazotization using HBr, you'll get the bromide. And if you treat that with copper bromide, heat, warm, you will get the bromide. And if you take, let's do another one. Supposing you take this compound, you can diazotize it. And if you treat that with copper cyanide and heat the mixture, then what you do is you replace the diazonium unit by a cyanide. Now you notice I haven't given you any mechanism. I've just given you the recipe. And the reason for that is the mechanism's horrendously complicated and differs for different types of compound, and people are not sure about what's going on. So we won't worry about the mechanism. All you need to know that if you've got a diazonium salt, treated with copper chloride, you replace the diazo group by chlorine. Treated with copper bromide, you replace the diazo group by bromine. If you treat with copper cyanide, you replace the diazo group by a cyanide. Now, I've covered the cyanide, I've covered the bromide, I've covered the chloride, but obviously I haven't covered them all. So let me just tell you about the others.
Yeah.
The only thing I've listened to lately is Justin Bieber.
What's that bad thing? Holding
If you
Does it
make
look good? What is I am?
Supposing you have this compound and you do the diazotization with sulfuric acid, you will then get and now if you treat that with potassium iodide, you replace the diazo group by an iodine. Treat that with HBF4, and you then heat it. You replace the diazonium group by a fluorine. Now all these reactions are called Sandmeyer was an interesting fellow. Never took a PhD, but has become very famous. He has a set of reactions named after him. He worked in the laboratories of a few famous chemists, and then he spent the rest of his career in a pharmaceutical company. I think it was Geigy, which I suspect is now Novartis. So you know now how to make that and that. And so there are only two more that are left, and the way to do them is as follows. So you can replace diazonium unit by an OH group if you heat the compound with copper oxide. And finally, if you treat such a substance with H3PO2, you replace the diazonium unit by hydrogen. So in the last few minutes you can see I've actually given you a heck of a lot of information, because what I've done is to tell you, you can take an aromatic compound, nitrate it, reduce the nitro group with either catalyst and hydrogen, or with iron and HCl, so you get an amine, and the amine can then be diazotized by treatment with sodium nitrite and either HCl or sulfuric acid, and you can take the resulting diazonium compound, or HBr. You can take the resulting diazonium compound, you can convert it into a chloride, or a bromide, or an iodide, or a fluoride, or something with an OH, that's called a phenol, or you can replace the nitrogen unit by hydrogen. So there's a huge amount of stuff that you can do via the diazonium salt. And the diazonium salt, they almost always come from a nitration of a benzene. So now you can see why nitration of benzene was such a big deal, because it leads, by a reduction to the amine, to a whole range of other compounds. Many of these compounds are very, very useful. I haven't told you about the mechanism of these Sandmeyer reactions and various modifications of them. It's all very complicated, we don't need to know. But we do need to know how to manipulate the compounds. Now I want to show you how to use this sort of information in what's really a very sophisticated case.
I know there's so much. I thought the lab items would be that, but now that we got the actual things that we have to remember to use. I don't know, for me, I just memorized it. I don't
Synthesis
know
is
why I
gonna
use it. No, use it.
and then it's gone like the day after this again. Don't crazy work.
Don't. Oh my, not gonna.
Supposing you need that compound. You recognize it's a benzene ring with a bromine on it, and it's a benzene ring with a methyl group on it. You know how to put bromine on benzene rings. Well, you can do electrophilic aromatic bromination. But if you've got a methyl group already on the benzene ring, the bromination will go also and para to the methyl group. This bromine's meta. So maybe you could put a methyl group on the benzene ring. So if you stop with bromobenzene, can you alkylate it? Well, the answer is yes, but the alkylation will go also and para to the bromine. So you've got to somehow overcome the directing effects of each of these groups. Now, one of the ways of doing that is to start with the aniline. Now, can you get your hands on this compound? Well, the answer is yes, because the corresponding nitro compound would result from paranitration of toluene. Toluene is just methylbenzene. And the methyl group directs ortho-para. So if you take toluene and do a nitration, you'll get ortho-nitrotoluene and para-nitrotoluene. You can separate them and get the para-nitro compound, which you can then reduce. So you can get your hands on this. If you compare this with what you want, you realize you've got to put a bromine there, and then you've got to get rid of the nitro, of the amino group. And so, on the basis of what I told you, you just say to yourself, oh, goody, goody, I know how to get rid of the NH2, because he just told us. Hypophosphorus acid on the diazonium. What about putting the bromine in here? Well, this stuff is an ortho-para director. Para positions block. These two ortho positions are identical by symmetry. So this group will direct a bromination here. Now, there's a little bit of a problem. If you add bromine to this, you get over-bromination. So you want to tame this a little bit. And what you do is you make the amide by treatment with acetyl chloride. Again, an experiment, the process you know about. Now you can do the bromination, and it will go exactly where you want it to go. Now you want to get rid of the nitrogen, and you need, obviously, a diazonium salt. Now, to make a diazonium salt, you need the amine. You've got the amide. And so what you do is you hydrolyze this. Use sodium hydroxide. Now you're in business. Sodium nitrite, sulfuric acid, that gives